Okay, so what we did is we're looking at the back page of the notes. We're doing regression with inference, meaning we're looking at two samples, which is kind of making sense because that's what we've been looking at for the last 3 or 4 weeks. We have a regression recap page that you can use to help you out. This clearly states the things you're supposed to pay attention to and the things you're supposed to ignore. Now, remember, when we did this in September, this is all we cared about, right? We didn't pay attention to anything over here on this side whatsoever. It was all to us a waste of space. But now we know what T stands for. What does T stand for? It's my T value, my test statistic. Okay, it's not the one we're going to use later today, but it's there for a reason. And then this means P value. So this is our P value. Again, this is not the one we're going to use, but it's there for something else that we need it. So these are used for inference questions. Again, we're going to adjust it and do our own thing. This one here, it will be something that we'll use on our other example. This is our standard error. This is the standard deviation divided by the square root of n. That's what that answer is. All right, so if you go back to your formula, when you find your test statistic on these samples, remember it's T equals the standard deviation divided by the square root of, or all that stuff. The very denominator part was the standard deviation divided by the square root of n. That's the number right there. You don't have to sit there and calculate it. So when we get to the back part of this, we'll use it. Here's your formulas on here to remember. Again, we never use R squared adjusted. We'll only use R squared. And here's all your sentences. So we're going to go ahead and go through these based on this one. And we're going to go through and kind of see. So here's the formula. Y hat, remember, this is a predicted Y, equals A plus BX. So I need to know what A and B are. So A is always my Y intercept. And B is going to be the slope. And then X is this variable right here. So for my first part of the equation, there's my answer. So Y hat equals 87.12 plus 1.5433X. Please don't forget to define your variables. Let us know that X stands for the height in feet and Y equals the volume in yards cubed. Stop me if you guys got questions on this, please. This has been since September. So we're dusting off some brain cells that we haven't used in a long time. This was well before all the sampling and experimental data stuff and well before probability and all that fun stuff that you guys are like, no, Mr. G, no more. All right, so what is the correlation coefficient? This is my R value. What this will tell me here in a minute is how strong of a relationship I should expect to find between my X and Y variables. So I get this from the R squared value. All right, since I don't have an R, I have to use R squared. So that's R with a little 2. So convert it to a decimal number, 0.358, then take the square root of it and get 0.5983. So is this supposed to be positive or negative? Positive. Okay, how do you know, Laura? You are correct. But for the rest of the class, you just took a guess and got lucky that it was positive. How did you know that it actually was positive? You already said? So Connor over here said it correctly. The slope is positive. Because whenever you take a square root of something, I know algebra is not necessarily our favorite subject, but if you remember, whenever you take a square root of something, it's always plus or minus that answer, right? Because in theory, you could have 2 negatives or 2 positives to get you that number. So the only reason we know that this is positive is because the slope up here is positive. These should be the same symbol. All right, very good. So you guys do remember a little bit. What is the coefficient of determination? That's already provided to you. That's what the R squared is by itself. So 0.358. All right, so any questions so far on just my numbers? Again, everything comes from my computer generated output. If you guys get to college, you get to use these things. They're nice. They're very helpful. You just type in all your data, you press enter, it does all your work for you, and it spits out this thing. So this is how people can look at thousands, if not millions of data points instead of the 15 to 20 that we deal with on our calculator. All right, so we need to make some interpretations here. We need to interpret the slope, the correlation coefficient, and the coefficient of determination. Your sentences are right there in your notes. So for the first one, for the slope, this one's my slope right here, 1.5433. All right, just fill in the blanks. For each increase in the height, and that's my X variable, of 1 foot, that's by how much? It's always by 1 measure of unit. There is a predicted, this is your key word that gets you all the points or loses points. There's a predicted increase in the volume by 1.5433 yards cubed. All right, so I'm just copying that straight off of my little guide there. All right, for the interpretation of the correlation coefficient. All right, that's the R value. We need to be able to determine strength, direction, and whether or not it is linear. Well, the easiest one to answer is yes, it's linear because we're not dealing with a set of data. And I didn't ask you guys to plug it into the graphs like we did in unit 2 and see if there's any curves. So we didn't test any residual plots on this one to determine if it's linear or not. So we're going to go with that it's linear. But the real question is, what kind of strength are we talking about? What did you guys put? Moderate, very good. Do you remember all of the breakdowns, Laura? 0.8 or higher, 0.8 to 1, either positive or negative, very good, is strong. This one fits into moderate, which is from 0.5 to 0.8. And then weak is anything from 0 to 0.5 in either direction. So very good. So if you need to write those down under your little strong, moderate, and weak, you can, but it's 0.8 or higher, 0.5 to 0.8, and 0.0 to 0.5. So that's the hardest thing to remember is what your strength is. So there's a moderate. Hopefully you put positive because both the R and the slope are positive. Linear relationship between, and then your two things, height and volume. Very good. So you guys do remember a lot of this stuff. Excellent. All right, what about the R squared? The coefficient of determination. What the heck is that telling us? Well, our sentence says the percentage of it, which is 35.8% of the variation in height, can be explained by the approximate linear relationship between height and volume. So both of these things kind of measure the same thing, and they kind of say it a little bit differently, and one can be more helpful than the other depending on what we're looking at. So this one in general is just looking at about the straight up linear relationship between the two. This one right here is saying that we can kind of explain all of the different Y variables we get. We can explain this percentage of them based on the relationship between height and volume. So this is a very kind of loose correlation, right? So R squared can be used to kind of determine overall how well your X variables are causing a change in Y. Again, we have to be careful. It's not really causation. Like we're not saying that height is directly causing volume to increase, but we can kind of say that based on what I've plugged into my formula, the X values I have caused this much variation in my Y. So if I were to be taking this a step further, which we will never do in this class, I could go into multilinear regression, which is more than two things, and I can add in extra X variables, like a second or third one, and try to get this percentage a little bit higher. But for this purpose of this class, we will never do that. It's just letting you know how much a Y changes kind of based on what your X variables are. All right, for the residual, I saw this is the part where most people left things blank or were thinking. So with residual, you take your formula and you plug in the X that they give you. So this is the X variable they got, and this is the actual Y variable they got. So I'm going to take the 60, plug it into my equation. So I got negative, whatever it is, 87.12 plus the slope times 60, and I get 5.478 yards cubed. So this is my predicted Y. Based on the measure of the tree, height-wise, the volume should be this. But in real life, that actual tree was 7. So there's a difference there. There's a residual, right? The formula for residuals is Y minus Y hat, which means the actual value minus what you thought you were going to get, your predicted value. So I put the 7 into the first part minus the Y hat, and this gives me my residual for my yards. Now, notice it's positive. So that's going to help us with our sentence here in a second. The actual volume of the tree was this much more above what I predicted, because I got a positive number. Had I had a negative number, then we would have said the actual volume is that much below the predicted volume. Does that make sense for the above and below? All right, how do we do overall? What do you guys think? Remember, most of it, you don't have to be an expert on all of it, but most of it, you can get through this again if it shows up on an AP exam. Because remember, stuff from the fall is going to be on there too. It seems like forever ago, I know. It's a good thing we're going to start reviewing soon in about a week and a half. All right, questions from me on this before we actually go into, okay, why are we doing this again, Mr. G? It's not just to torture me. I know there's a purpose behind it. There is. We're going to actually do a confidence interval and a hypothesis test with this data. Questions? All right, still see a few people writing, so I'm gonna give them a minute to make sure they got all of the phrases and words and symbols. Please, 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 when you're doing this, do not forget your units. They will count off for that. We'll count off for that. Units are very important. So if it's yards cubed, put yards cubed. If it's feet, put feet, whatever. Just don't forget to put your units. Miles, inches, seconds, whatever it's talking about. And always define your variables. So the very first part where you write your equation, please don't forget to tell me what X and Y. Okay, so let's look at the back. We're gonna do this one together, so you don't have to just see it on my screen. So same set of data, same beginning step. It has added in some useful information for us so that we can kind of pay attention to what we're doing. It actually tells us how big our sample size is. So n is equal to 20. We're gonna need that. It's not obvious. It took me like 30 minutes on Sunday to read it. And I kept skimming over it. So it's right there. You guys are probably like, come on, Mr. G. Sorry. It was the weekend. I wasn't paying attention. This number here we're going to use in our formula. Again, this is our standard error, or basically the last part of our equation to find t. So we won't have to do that. We can just plug this into the calculator. All right, so basically, here's something important to know as you guys are going through this. You will potentially be asked to find a confidence interval for the slope, which is not something we've done in class before, or perform part or all of a hypothesis test for the slope. I mean, why not, right? It's a variable. We can test it. We can find confidence intervals on it. Based on our experience giving this exam and seeing this exam in the last multiple number of years, this will likely be a multiple choice type question. We've never seen them use the assumptions for the regression inference on any part of the exam. So we're not going to do that now. If they haven't done it before, we're not going to expect it. So when you do this confidence interval hypothesis test, you just have to go straight into your calculation, because they've never asked that before. And I'm not saying they never will, but in the 15 plus years they've done this exam, that's never come up. Remember, regression is based on a sample of the population rather than the entire population, which is what this is, right? This is based on 20 trees. So therefore, we're gonna have two different symbols. The sample slope is the lowercase b, and the population slope is gonna be the beta symbol. Right? Because why not? It's the same as type 2 error, so let's confuse everybody. This is only so many letters, we need to use it again. Our degrees of freedom for all of this are going to be n minus 2 because there are two variables, x and y. And our confidence interval is going to be this equation. The sample slope plus or minus the t times the standard error, ding, ding, there it is right there, of that slope. So we're going to find and interpret a 90% confidence interval for the population slope. So the first thing we need to do is start with our sample slope. So that's going to be 1.5433. That comes from the right here. That's my sample slope. So this is little b right here, if you need to write it down to remember. All right, I'm using this formula right here to calculate my confidence interval. So this is plus or minus the t-score. All right, well, to find the t-score, we're going to have to use the old program in the calculator, not the fancy new ones. We're going to have to use the inverse t. So we're going to go to second, bars, and go to number 4. All right, we're going to press enter. We got to type in the area that we want and the degrees of freedom. All right, so we know that degrees of freedom for this is going to be 18 because we have 20 for our number of trees minus 2. And then our area, we have to make sure we type it in right. We want a 90% confidence interval here. But remember, when we use this program, the left half of the graph or the left tail needs to be added into it. So we need to make sure we put in 0.95. All right, so to find my t again, if you guys need the formula reference later, it's going to be going to inverse t and typing in 0.95 and degrees of freedom as 18. So this is, I'm putting this down here as reference so you guys can see it. All right, so this is my t that I'm going to use for my confidence interval. So 1.7341. Everybody okay with that? And I got what? Say it again. B. B is from the readout. Yeah, it's the slope. So this little b stands for sample slope. And so from the sample of 20, this coefficient in front of it, that's the slope. So if you look at your little, okay, yeah, got it. Okay, so now we got to finish off the problem. So it's this plus or minus the t-score, which we got, times the standard error of our slope. So we don't have to do any calculations with this. We can if we want to, but we don't need to because it's right there. The standard error of our slope is 0.3839. So again, what's nice about the computer generated output is everything is kind of already there for you. And now you can go through the equation here and type in your stuff. I do the minus first because I like the lower limit first. All right, so there's my lower limit or my lower interval, if you will. So this is 0.8776. All right, and then for the upper interval, I can just copy that again because I'm lazy and change this to a plus. And I'm gonna get 2.2090. All right, again, are we okay with this? We just did our confidence interval, like outside of writing the conclusion, we're done. Did I lose anybody's anybody got any questions? All right, then we can write our confidence interval. It's mostly the same. The sentence is just a little bit different because we're talking about slope, but it's not too crazy that we can't figure it out. So we're going to say we are 90% confident that volume increases. This is where it's just a little bit different, or a little bit different than what we did before. On average, and then we can just sum up what we found out between 0.8776 and 2.2090 yards cubed for each 1 foot increase in height for trees. So basically, we're stating the interpretation of the slope in our confidence. I'll leave that up there a second so you guys can write that down. So we are 90% confident that volume increases on average between those two numbers for each 1 foot increase in height for trees. So this basically is like the interpretation of the slope combined with our confidence. Word for word is not as important as is that you have something about the slope in there, because that's what we're talking about. All right, any questions on the confidence interval? Shouldn't be anything hopefully too earth-shattering different. All right, for this last part here where we're doing our hypothesis test. When doing a hypothesis test for the slope, what we're testing for is to see if the population relationship between X and Y is positive or negative. Meaning, we're looking for what? Some sort of change or difference between those two variables, right? Just like we've been doing with our chi-squared, just like we did with unit 7 when we had all those percentages. So we're testing for that. If it could be either one of those, that would mean X and Y do not have a good relationship. So say back here on my interval, if I got both a negative and a positive number, that would be a red flag. 0 is somewhere in between there. There may be 0 change in height versus volume. That means my relationship is trash. There's nothing there. So the fact that I did get all positive numbers or potentially all negative numbers had it been the other way is a good sign that I've got some sort of relationship there that's happening. There is some sort of change or difference between my two numbers. All right, so when we're doing our hypothesis test, we are seeing if the slope is potentially equal to 0, basically, which ding, ding, ding is what we did in unit 7 and what we're doing with chi-squared, meaning that there would be no relationship between the two. Or if the slope is definitely not 0, meaning that there is some sort of relationship. That's all we're doing with this stuff. So just as you guys are going through this, keep that in mind. We're testing to see if our relationship is actually relevant. So that means every time you do these, if you're doing one for a slope, then your original hypothesis is going to be there is no relationship, right? When I see two random variables in front of me, my original assumption is nothing existent. What I'm going to test for is that it's not 0, that there is some sort of difference between these two, that there is some sort of relationship. And then we just have to define what our actual slope is. For our t-score here, we have this formula. Again, this number, and this number, they're already provided to you. So you just have to sit there and plug things in. And then to get our p-value here in a second, we're going to have to go back to our friend TCDF, which is option number 6. Some of us forgot this on our test. And plug in our lower bound, upper bound, and that our degrees of freedom are n-2, which again, on this particular problem, n is going to be equal to 20, and that's from above with all the notes. Okay, so let's do the hypothesis test now that we kind of know what is happening with our setup here. So again, we're gonna forego and skip only on this example. Please don't think this is from now on. Just on this example, we're not gonna waste our time with the assumptions because they've never asked for that before. All right, so what is our hypothesis? All right, we've got two things. That our original null hypothesis is that it is equal to 0. And the thing that we're hoping to find is that our population slope is not equal to 0. So right away, we already know what kind of test we're going to be doing, right? A two-tailed test. Which means once I get my p-value, please don't forget to multiply it by 2, because the calculator will not do it for us. We're not using the fancy program for this one. All right, let's define what our b is in this case. So we're going to say where b is the population slope for change in volume over change in height for trees. So again, I'm just kind of defining what my slope is. It's the change in volume over the change in height, right? Y over x. Change in y divided by change in x. See, you guys never thought that algebra 1 lesson was going to be so important. All right, so let's do our calculations. All right, we got to find our t first. So again, using this formula right here, we know all these answers. So little b, sample size b, that's going to be my 1.5433 from the computer generated output. The large b there, or beta, is going to be 0 because that's what my hypothesis is. I assume that there is no change. So basically, we're trying to determine if these are far enough apart. And then you could do standard deviation divided by n, but you don't have to. This bottom part is the standard error of your slope, which if you go back up to your chart there, is that same number we used earlier, the 0.3839. So I didn't have to really do anything in the calculator. Everything's kind of provided to me. I'm just kind of plugging and chugging on this. All right, so let's go to a fraction, type everything in, 1.5433 minus 0 divided by 0.3839. Now, before we go any further, here's the fun part. See that number? 4.02, whatever. What do you see right there? Ta-da! So it's actually already given to you. So that's what that t is. Okay, so this one's for when you do the hypothesis test. So that's your actual test statistic. It is not the t that we used here. So please don't get those confused. Two completely different values. All right. So because we got a positive number, this is going to be my lower limit. If you remember the trick from before, this will be on the right side of the graph, and I'm going to test that it's going to the extreme right. And then whatever I get, I'm going to multiply it by 2. All right, so we need to find our p-value. So remember your degrees of freedom are going to be 18. What else we need to write? Okay, p-value. So that's going to be second vars, and this is where we go to number 6, TCDF. We've used it before. Oh, I draw one second. Second vars, TCDF. All right, so again, this one's going to be our lower limit. I didn't write out my answer, I'm sorry. 4.02. What was the thing? 0201. All right, my upper limit's going to be infinity because we're going forever in the right direction. Degrees of freedom is going to be 18. Paste it. What do we get? 4.01 times 10 to the negative 4. So just so you guys know, we need to multiply this by what first? 2, because this is a two-tailed test, right? So my final p-value, so I got 0.0004 times 2. So my final one is 0.0008. That's my final p-value. Okay, again, scroll up to the top real quick. What do you notice? It only goes to 3 decimals, but what do you get for a p-value? Nothing. Okay, so our p-value was so small that our computer-generated output just kind of went, meh, you don't need it. And so it didn't give us anything, but it's still there. All right, normally, since there's nothing here, we would do alpha at 0.05, right? That would be our default alpha. But if you think about it, since we're testing this at the same confidence, we're using the same confidence interval, since we used a confidence interval of 90%, what should our alpha really be if we want to do this right way? 0.1, right? Because we used 90% for our interval for the middle part of the data. So how much is left over for both tails of the data? We're going to use 0.1. All right. This is the part where some of you guys are still missing stuff on the questions. So again, one more time, for those of you guys that are still like, what did Mr. G do again? 90% confidence interval means we want the middle 90% of the data on our graph, right? What's the lowest and upper limit of the middle 90%? If I want to test it at the corresponding alpha, then we should use 0.1 on this one. Why? Because it's a two-tailed test. So I'm going to use both sides of the graph that are left over. So there's 5% on either side. 5 and 5 is 10. There's my 0.1. If it was a one-tailed test, we would have done this. Are we okay with that? Because this is the question that still gets you guys on the multiple choice stuff. When I go, hey, Connor, I'm going to give a 93% confidence interval, and it's a one-tailed test. What should my alpha be? You got to go back through and you got to figure out what your difference is and multiply by 2. If it's a two-tailed test, then it's just what it is. All right. So keep that in mind as you guys are going through. All right. Any questions on our numbers here? What are we going to do with this? What's our p-value? It's less than or greater than alpha? Less than. Very good. So that's going to be our conclusion. Let's see if I can fit it all in here. For whatever reason, when Ms. Nichols makes this, she makes it very tight. All right, so there's my conclusion. Let me get my fancy paperweight set up so I don't have to hold it. All right, so since the p-value is less than alpha, we reject the HO. All right, so what does that mean to us? What does it mean? We reject the HO. We rejected that that's equal to 0, meaning we found enough evidence, that's what we're going to say in a second, that there is a change in our relationship between these two things. So there is sufficient evidence to say, sorry, I'm writing kind of small, so it'll all fit in here. There is a relationship between, and what are our two variables? Height and volume. So basically what we did is we got a slope from a computer generated output. We found the formula, we interpreted, sorry, I'll speak English, all of our garbage there. And then we're like, okay, everything looks great. And then we ran a confidence interval because we know it's just a sample of 20. So what could we expect the population's actual slope to be? That was the first part of the back page. And then we said, okay, so far everything's showing up as good, but let's run a hypothesis test just to make sure, let's be extra thorough and confirm that without any reasonable issue, that there actually is something not 0 in between those two things. And that's what we found. We got a very small p-value, which is good for us. And that meant that there is evidence to show a relationship does exist between height and volume. Another way you could write this, if you guys want to use an alternative way, you don't have to write this down if you want to. But another way you could write this is heights of trees. And this might be like how they phrase it. So that's what we're going to put this on there. Can be used to predict volume. All right, so this is an alternative phrasing of this conclusion. So heights of trees can be used to predict volume. So we had these two random variables. We squished them together. We saw some slope stuff happen. We saw some R values show up. We saw some R squareds. We went through all of our stuff. And we went, okay, We know how to do that, Mr. G. Now what? Well, let's run a confidence interval and let's get a guess on what the true slope is going to be for these two things. And it came up where both variables were above 0. So awesome. Everything's looking great. Let's go ahead and do our hypothesis test. Again, p-value comes up really small. So we're good. There was no 0. We've confirmed it. And so one of these two conclusions you guys can use. Again, this is the way we've written it all year. But you never know with those multiple choice questions. So in case it says something like that, you guys can say, yes, we can actually use heights of trees to predict volume. Remember, this is just a correlation. I did not run a well-designed experiment to where I can actually say heights does cause volume to increase. So just be careful. All right, guys, that's it. No mas on the notes front anymore in this class. The rest of it's all you guys do. Questions for me? Guys, just so you know, I've been like my quietest class all year. Not that it's a good or bad thing. Just nobody talks. Okay, so let's look at the learning plan for the rest of the week and a half here that we have coming up. So today was the 12th. We did our regression review notes. You guys will have the rest of the class, which is almost like 45 minutes to work on this homework for the regression. Any homework from the chi-squared stuff you didn't finish, if you haven't started the chi-squared activity, you can do that because it's not due till the night, so you still got time. And then on Wednesday, we'll have the FRQ. I'll load up the FRQ stuff here a little bit later today, and you can start working on the FRQ stuff during class. At the end of class on Wednesday, we'll go over the two that everybody wants the most help on. So I'll ask you guys what were the two hardest, and that's the ones we'll go through. And then Friday, because Thursday is another one of those test days, but it's an A day this time, then we'll have more time in class on Friday just to work on stuff. So I'm hoping you guys don't have too much homework for me at all this year. Like if you just do most of your stuff in class, you should be good to go home and just like relax from this class. I can't speak for your other classes, but for this class, you should be. We are going to have our usual FRQ, Albert IO, and there is an optional mixed review. I would suggest you at least look at it, not so much so like if, Claire's busy, she's got a life and stuff to do. She doesn't have to do every problem in the mixed review, but maybe she wants to take a minute and check and see, can she at least identify which test she's doing? All right. And then she wants to work it past that, that's up to her. But maybe she sits down and she looks at that mixed review on there and goes, oh, that's chi-squared for goodness of it. I know what I'm doing. Or that's chi-squared testing for independence. Just so you know, right? But when you come to the test, you have to identify which one you're doing first. Then the rest of it's just calculator work. It's easy. So if she doesn't want to do the actual math, I get that. I mean, we're at the point of the year where we're all tired and we've got stuff we'd rather be doing. 100% understand. But I would say it's at least worth a look to make sure you understand which type of test. Just as a suggestion, because that's how we're going to ask questions and stuff. I've heard that the Albert IO is a little bit more lengthy this time, but I'll still kind of make a video. Hopefully this week I'll get to it so you guys have some more time to watch it, because everybody gave me lots of positive feedback about the video last time. And then next Tuesday, so a week from tomorrow, will be our very last unit exam, Unit 8 test part 1 and 2. One will be multiple choice and one will be FRQ. And then that's it, guys. We're in like full on review mode. We got seniors doing it on paper and some juniors that have switched over to paper in May. And we've got other students doing it digitally in June. So we'll be practicing both methods. I heard a rumor that the app for the, the digital version released, but it's a hot mess because if you're borrowing like the school's computers, then it's not installed on there yet. So don't panic. You don't need to have it installed by today or anything. We're gonna have plenty of time to look at it, get you guys logged in. Remember, it's not till June, the digital one. So if you're taking the digital one, take a deep breath. It's like 2 weeks, it's like 2 months from today. All right, so you got plenty of time to get everything ready to go for those of you guys doing the digital one. And for those of you guys doing the paper one, we already know how to get you prepared for that because that's how it normally is. So don't panic. Ms. Holmes said everybody was going into her office and like, I can't install the app and my history teacher's making me. Okay, well, just tell your history teacher to relax. It's not ready to go yet. So anyways, any questions for me? Almost there, guys. Less than 6 weeks. All right. You have the rest of the class to work on what you need to work on. I am here at your disposal. Ask away anything that you would like assistance with. Otherwise, I'm going to sit here, shut up, and work on grades and stuff, and let you guys work through whatever you need to. My classes work or other classes work or whatever. You guys got a good 40 minutes here of productivity time. Please use it wisely. A lot of you guys have some makeup work and catch up to do, so I'd be working on something. All right, guys. Have a good day, Zoom people, unless you got questions for me. All right, Mr. Connor, what you got, man? Yeah, you want to? Okay. Not at all. The Zoom people are gone. What's that? All right, so modules, chi-squared activity. If you guys don't want to do this, just put your earbuds in and watch your Netflix or something. Where'd I put it? There it is, chi-squared activity. So after I got all of your guys' survey stuff filled out, and I'm sorry this wasn't ready on Thursday for you guys that were ready to go. I had to fudge some of the numbers because the expected values didn't work out right. We don't have apparently that many left-handed, left-eye dominant people. So I had to make up some people. So if you look at it, like 19 people are left-handed. No, it's like 6, and I had to like go in there and add the numbers into it. So I had to make the expected counts equal to 5, or somebody like Connor who's sharp would go like, Mr. G, I can't do this. So now you got to do them all. All right, so for this first one here, question number 1, do you think that people are born on some days more than others days of the week? Below are the results for Mr. Jennikin's survey of 79 students. So you were born on a Saturday. Okay, so you're one of those 8. So the first question is, what are our expected values going to be? What do we do in this situation? What do you guys think? Yeah, you take your 79 AP students there and you divide it by 7. Exactly right. We would expect every day to be equal. Oops, sorry, I didn't mean to hit that button. Wrong button. I meant to hit this button.